Alright, welcome back to chemistry, welcome back to school. I hope you all had a wonderful April break. And we've just finished up weather, amazingly, very quickly, going through all the gas laws and how gases behave when looked at through the lens of chemistry. From now on, we're going to be talking about the fifth and what was in your syllabus final unit, fire. And fire is relevant because this is a unit all about energy and what we call thermodynamics, which is kind of the branch of chemistry that talks about energy in compounds, energy in reactions. So, just to begin, the question is, how do we talk about how energy changes in a process? And it doesn't have to be a chemical process, though we will talk about it that way too. It can be a physical process, so what does it mean when something gains energy? What does it mean when something loses energy? And this section is going to be about lessons 5.1 and 5.2. There are also a bunch of kind of qualitative, conceptual questions in the thermodynamics exercises, which are not the required assignment for this week, but I still recommend that you take a look at them. Okay, so before we begin, we've got to have some definitions, just like you can't talk about atoms without talking about protons, neutrons, electrons. Can't talk about energy if we don't really know what energy and temperature are, for instance. So when you think of energy, you might think of a lot of different things, but the most general form of that definition is, we call it the ability to do work or heat something up. So energy, remember way back in alchemy we talked about what's matter, what's not matter. Everything that's not matter or empty space is probably energy. So things like light are energy, things like fire are energy. There are a lot of other examples you might have heard of. Kinetic energy or potential energy, these are also forms of energy as well. And so one thing you might have heard about in biology, I'm not super sure, is that there is something called chemical energy. So chemicals also have energy. And how does that work? Basically, if I have a compound, can I draw on this? So if I have a compound with some bond there, let's say this is like oxygen or something, so there's a double bond. If I break up that molecule, you might expect that some energy gets released or maybe absorbed. I don't know what your intuition is, but chemicals have energy. On a side note, if you've ever heard of E equals mc squared. Okay, I don't think this Google Slides likes me, but E equals mc squared, that's saying that mass itself has energy. If you use if you convert mass into energy, like stars do, you can turn matter into energy, which is kind of crazy. But chemical energy, again, is the energy in a bond. So the energy of the bonds of molecules or compounds. So what a chemical reaction is a reaction, something happens and bonds break, right? And if you don't see that immediately, think about a reaction, draw out the molecules for it. One substance becomes a different substance. That's because there were bonds that were breaking and reforming. So if I had this oxygen over here, and I don't know, it reacted with something, let's say that it combusted something, so it broke a CH4, methane. And you know that in combustions, you're going to make H2O and CO2. See how the bonds literally broke and reformed. Like, this bond between the C and the H here no longer exists. It must have been broken, and then new bonds formed. So, in chemical reactions, atoms are rearranged, and so the energy will change. The system, which is this reaction right here, will have a different energy at the end of it, because maybe the energy in this CH bond is different from the energy in that CO bond. Okay. So, conservation of energy. you may have heard of it before. So conservation of energy is the idea that energy cannot be created or destroyed. And that's what this orange box here says. Sometimes in chemistry, we call that the first law of thermodynamics. If you've ever heard of the 3 laws of Newton or of Kepler, there's another set of laws about energy called the laws of thermodynamics. There are 3 of them. But the first of these just says energy cannot be created or destroyed. So, as I was saying earlier, thermodynamics is a part of either chemistry or physics. You'll probably have to take it in either major. That talks about the relationship between heat, which is a type of energy, and other forms of energy. It talks about how energy is converted to and from other forms. So basically, energy is always conserved. It can never be created or destroyed. That means all the energy in the world, whether the energy that's powering light bulbs, or the energy you use when you walk, or anything like that, the energy you use to heat up your room or something, all of that came from somewhere else. Energy always exists. It never gets destroyed. You can never make it out of nothing. You can only convert it between different forms. And that's what thermodynamics studies. And we can measure the change in energy of a process. So if in the beginning I had, let's just say, 50 energy in my products, we'll get to units in a bit, and later on I have, 100 units of energy in my, did I say products? 50 in my reactants and 100 in my products, it means this system, it can't have made that energy from nothing. You might need to take in some energy from the environment, like 50 energies appeared from the environment. I'm sorry this pen is so bad. It's the only way I can present and write at the same time. So that's what we mean by change in energy. Here there's a change of 50 units of energy. And you can think of that as a formula if you'd like. You can also just kind of draw that little picture I just made, but the change in energy is the energy of the products minus the energy of the reactants. That big fancy symbol here, this is just means add up. So add up all the energy of the products and then subtract the sum of all the energies of the reactants. So if there was a total 100 energy at the end and 50 to start with, 100 minus 50 is the change in energy, in this case 50. Alright. Throughout this slide deck, as always, there are these concept checks. I've gone ahead and made the concept checks into exit tickets for each section. So you can take out the exit ticket and work on it alongside this lecture if you'd like. Pause the video, answer the question, but go ahead and try it out on your own. Alright, so in this case, what's the change in energy? Again, I can think of it as a formula if I want. I can also just kind of draw the picture and think with common sense, but what's the change if at the end the products are 300 kJ, that stands for kilojoules, like kilometers, kilometers. Joule is a unit of energy, and you can make, there's 1,000 joules in a kilojoule. So 300 minus 100, so it should be 200 and it's positive. So B. Alright. So again, this is a picture of what we had earlier, the same formula. The change in energy is the final minus the initial, or the products minus the reactants. And we always want to make sure that energy is conserved. What that means is that the energy of the system, which is the reaction that you're measuring, this green stuff here, the system, if energy goes in, we consider that positive because you're adding it to the system. And when the system loses energy, it has a negative sign if it goes to what we call the surroundings. So whenever you're conducting a reaction, you're measuring the energy involved in that system. But you also have to consider the surroundings. The surroundings is literally just like everything else. Surroundings is everything else, so like the air around the flask, for instance. Because energy is conserved universally. The first law of thermodynamics applies to this whole thing. It doesn't just apply to one part of it. So the beaker is allowed to lose energy as long as the surroundings takes it. Energy is just being transformed from one place to another, one form to another. And depending on whether we gain or lose energy, we have different words for this. If the change in energy is negative, that means your system lost energy. That means energy is coming out of this beaker, right? Energy is coming out of the beaker. That means the beaker is going to feel hot. And we call that exothermic. It's coming out. On the flip side, if we're gaining energy into the beaker, that means heat in the air is going into the beaker, so it feels cold, and it takes it in. Endo, like, I don't know, exoskeleton, endoskeleton, endothermic. Endothermic means it's taking in the energy. So this is, again, just some definitions. So I said earlier that it doesn't have to be just for a chemical system. We can talk about change in energy for physical changes as well. In this case, phase changes. So exothermic phase changes, take a moment to pause and think about what that would mean. Which phase changes are exothermic? So a few examples would be freezing, or condensation, or deposition. Deposition is the opposite of sublimation. But again, freezing, if something goes from liquid into a solid, what does that mean in terms of the energy involved? Which one has more energy, a liquid or a solid? At a molecular level, which one has particles that are moving faster? So if liquid has faster moving particles and then it became a solid, slower moving particles, it lost some energy. It went into the system. So it gave off heat, so it's exothermic. So, it's a decrease in temperature or kinetic energy, particle motion, and that's going to be, these are all exothermic processes. I wouldn't memorize this list, I would just think about it every time. On the flip side then, the endothermic ones are like melting, like evaporation, like sublimation, which is, again, a solid going directly to a gas, like dry ice. And the opposite happens. The kinetic energy increases in the system. You might be remembering that we had a kind of edge case about phase changes, dissolution or dissolving. Dissolving actually can be either, depending on what substance dissolves. You might imagine that something, quote, likes to be solid versus aqueous, and that will affect the sign on dissolving. Alright, so again, here's a concept check. It's in the exit ticket if you want to just do it there. Alright, and just to kind of talk about a few more examples, you might remember these equations from way back: respiration, which is how we get energy, all organisms, and photosynthesis, how plants can take energy from the sun and turn it into food somehow. So looking at these one at a time, so on the left here we have respiration. Just thinking about it, would you expect that to be endothermic or exothermic? I mean, I know it says it right there, but it says it's exothermic. Why? Because the system, this reaction, releases energy for us to use, for animals, plants, etc., to use that energy. It has to be exothermic. On the other hand, photosynthesis is endothermic because you can see that it's taking in some energy into the system, taking in like sunlight, right? Sunlight. Oh dear. Sunlight, taking it in, absorbing it, and then the products end up with a higher energy. See, this y-axis is energy here? The products end up with higher energy than the reactants. Therefore, it must have taken in some energy from the surroundings. The opposite is true of the exothermic reaction in cellular respiration. So just kind of a chart summarizing some of that. You can take a look and pause it if you'd like. Here are a few more concept checks. Again, I'll leave it to you to look at in the exit ticket a little more in detail, or you can pause it now. If you've already paused it, a hint would be to look at the temperature difference. Again, another question. Exothermic, meaning releases energy. This one relates to the previous question. Again, you can pause. You can always ask on Piazza or send me an email, meet up one-on-one. I'd be happy to answer. Would you expect combustion to be endo or exothermic? Why? And alright, that concludes lessons 5.1 and 5.2. If you want to get up, walk around, do some of the suggested questions, feel free to take that in for now. I know it can be a lot. No need to do it all in one day.